Chapter 5 here is all about the periodic table. We're coming to the periodic law, which explains why the table looks the way it does. A little bit of history, just so you know the name. Dmitri Mendeleev. He was one of the first ones who took the elements, the known elements of his time, and arranged them by similar properties. He started with order of mass, and then when he looked at them and they had similar properties, he then rearranged them, even though pulled them out of order of mass. This down here is actually what his original table looked like. A little bit different now. Obviously, we know a lot more elements, but if you can see some similarities, hydrogen here, lithium, followed by beryllium and boron. So he was pretty well on. Another guy to know is Moseley. Moseley is the one that came up with what we're studying here. Moseley came up with the periodic law. He was the one that took the idea of the number of protons being the atomic number. And then he went and said elements act a certain way according to their atomic number. They have periodic functions, which means they have a similar function depending on their atomic number. Okay, and you can see elements on the periodic table are arranged by both atomic number from left to right and top to bottom, but they're also arranged with similar properties. Think about the noble gases all the way at the end to the right. They all have similar properties. Okay, a couple slides of review. Valence electrons. If you remember, the valence electrons are the ones that are in the outermost energy level. These are the ones that are lost, gained, and shared when making chemical compounds. Okay, again, the highest energy level. So these are the ones that are going to be found in the s or the p orbitals, not in the d orbitals. If you want to know how many valence electrons, a quick, easy way is which column are they in on the s and p orbitals. Okay, if they're in column 2, like magnesium, they have 2 valence electrons. Chlorine is all the way at the other end in column 7, so it has 7 valence electrons. Another review from chapter 4. If you remember Bohr's energy levels, we're going to be talking about those different energy levels. Again, we know that the energy levels aren't all that exist. There are the orbitals, but they also follow the energy level rule. So remember this, how if you go up the energy level, you get further away from the nucleus, okay? And as you go down the periodic table, you're going up energy level because you're adding more protons, which adds more electrons to the cloud. Before we hop into the periodic trends, it's important to know we're going to look at 2 different trends. We're going to look at atomic size, and we're going to look at this thing called electronegativity. Both atomic size and electronegativity follow trends horizontally, which is across the top, and vertically. That's a V. So at the end of this video, you're going to have 2 different explanations for 2 different things, a horizontal and a vertical explanation. So you're going to have 4 explanations in your head at the end of this. Let's start with atomic size. Atomic size it's the size of the atom. This is the nutshell here. The vertical trend is going to be dependent on the energy level. A higher energy level is going to mean a bigger size. The horizontal trend is going to be all about what we can call proton pull. The protons are going to pull those electrons in the cloud, and more protons means more pull, so that cloud of electrons is actually going to get smaller and closer to the nucleus. We'll go through each one of these in depth. Vertically, so up and down. Like I said, a higher energy level, the energy level of N, means more electrons, and so those electrons are further away from the nucleus, which equals a larger size. Group 1, for example, we've got hydrogen here, just one energy level in hydrogen. Lithium builds up to the 2nd energy level. So here's the 1st energy level, builds past that, ends up at the 2nd. As you can see, it gets bigger. That cloud of electrons around it gets bigger. Sodium in the 3rd, so it's 1, 2, and 3. And so as you go down the periodic table in the same group, the elements get larger. So on the periodic table, I've got energy level 1 here, 2 here, 3 here. So as I'm going down, they're smaller up here, and the atoms are bigger here. Okay? That's the vertical trend. As the energy level goes up, so does the size. The horizontal trend, the left to right trend, again, it's all about that proton pull. Okay, so as you move across one row, if you're going left to right, you're looking in the same row. Okay, the atomic number is going to increase as you go to the right, which means a proton is added. Even though protons added and electrons added, that proton is going to have a strong pull, and it's going to make everything in that same energy size or energy level in that row get closer and closer. Let's show you. So let's look at row 2. We've got lithium, beryllium, and boron. Lithium here is in 2s1. Beryllium is 2s2, which means 1 valence, 2 valence, and boron is in 2p1. So we're going from left to right here. Okay. If you can see, each one of them in the second energy level. However, as I move from lithium, I add a proton, beryllium. Those protons pull that second energy level a little bit tighter. And as we go from beryllium to boron, that fifth electron or fifth proton pulls them even tighter. So they're all in the second energy level. But as you add more protons, they pull those energy levels closer to the nucleus. So we actually get a trend that looks like, we're going to draw the arrow this way. Okay, and we're smaller here on the right, and we're bigger on the left. Okay, so again, the vertical arrow, small, big. Horizontal arrow is going this way. Small over here, pulled nice and tight, big here. There's your atomic size trend, both vertically and horizontally. We just showed it to you. Take a moment, try and explain the atomic size trend to yourself, someone around you. Electronegativity is the second trend we're looking at. Electronegativity, it's a new word for us. Electronegativity is the tendency for an element to attract electrons when it's bonding with another element. So when atoms bond, the electrons interact, and the one with a higher electronegativity is going to pull on neighboring electrons more. The vertical trend, up and down, it's all about closeness of the new electron to the protons that are pulling it. The horizontal trend, it's all about stability. We're going to talk about stability. Okay, so the vertical trend. This makes sense. The closer the nucleus is to the electron, the stronger pull it's going to have. We'll show it to you, but essentially, if I'm about a positive here and a negative here, and a positive here and a negative here, this one here is going to pull on that negative a little bit stronger. If you need an example, think about magnets. The closer you hold a magnet to each other, the more pull there is, the stronger that pull is between them. If I separate them really far, it's not going to have a very strong pull. Okay? So what this means a smaller atom is going to have a stronger pull because that neighboring electron can get closer to a smaller atom. So, same example here of group 1. If I've got a neighboring electron that's here, a neighboring electron that's here, neighboring electron that's here, the smallest atom is going to have the strongest pull because the electron is closest to the protons. So as the size gets bigger, the electronegativity goes down and gets less, and inversely, as the size is smaller, the electronegativity is higher. Let's draw this on. Okay, so remember, look at my vertical side. Bigger size down here, smaller size up here. That means our electronegativity is going to go the opposite way. A smaller atom is going to have a higher electronegativity. A bigger atom is going to have a lower electronegativity. It's going to have less of a pull on those neighboring electrons. Try and explain that one as it goes up and down. Okay. Horizontally, It's all about the rule of 8. If you remember the rule of 8 from bonding, atoms like to have 8 valence electrons, also from chapter 4. They like to have 8 valence electrons, except for hydrogen likes 2, but that's okay. So with 8, they've got a full outer shell, they're happy, and that's what they go for. Electronegativity is going to have a play in this, because if they are closer to getting 8 by pulling one, they're going to go ahead and want one really badly. Okay, so an element that can attract electrons to get stable is going to have a high electronegativity, but an element that it's easier to lose electrons to get stable is going to have a lower electronegativity. It's actually not going to want those electrons. If you look up here, the green numbers, I'm showing how many valence electrons are here. And remember, the rule is 8. They want 8. Hydrogen has 1, or everything in this group has 1 valence electron. That means it would have to gain 7 to get to 8, or lose 1. Chances are, and we've seen it in bonding, column 1 here would want to lose 1, and that would make them more stable. On the flip side, from all the way here in group 7, they need to add 1. Let's take that. They need to add 1. All they need is 1 electron to get stable. Okay? So they're going to have a really high electronegativity. They're really going to want an electron. Okay? I'll put an electron here so it doesn't look like we're positive. Okay? So as I go from left to right, you can see over here, really want electron? Not so much. Okay, don't really want over here. An example in a picture here, you can do lithium versus fluorine. Okay, if lithium, let's do lithium first. Lithium has, this is 1s here, and this is its 2s. It's 1s2, it's a full s, and 2s1, as we have here. If I'm able to lose this electron for lithium, I can drop it out of 2s and bring it down to the 1s, would make it full outer shell. Okay, so I lose my 1 electron, and all of a sudden lithium becomes Li+, but it drops to the 1s, 1s2. That's a happy full outer shell cation. Fluorine, on the other hand, fluorine only needs to gain 1 more. If you see, it's got 2s2, 2p5. So that has 7 valence electrons in the second energy level. Fluorine wants to gain 1 electron. So we see here, it wants to gain 1 electron so it can fill up the 2p outer level, our energy shell. So fluorine gains 1. It becomes, that should be fluorine minus, because it just gained electron. So it becomes F minus. And if you notice, we added a 6 here because we have 2 plus 6 equals 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. So by adding 1 electron, fluorine becomes more stable. So fluorine has a high electronegativity because it wants to gain 1. Lithium has a very low electronegativity. It doesn't want to gain, it actually wants to lose 1. So on the left here we have our vertical trend. As it gets smaller, the electronegativity goes up. As it gets bigger, it goes down. And lucky for us, this arrow is actually also opposite. As I go from left to right, it's got a higher electronegativity here and a lower. This has become very important when we talk about bonding and different types of bonding in the next chapter. 2 trends together right there, 4 explanations. Practice them, see if you can do them. Can you tell somebody else?